Hello everyone. So I'm recording this. I'm at my parents' house, so if you hear my kids or anyone in the background, that's why. And so we are talking about topic 1.6. And that's where we're going to be taking notes. And so please follow along with me. Go to page 34. All right, so on the AP Chem test and in the unit test, you're going to see these photoelectron spectrums. And there's a couple things that I want to point out to you. The first is look at the axis. Look at both of the axes, but then really look at something interesting about the x-axis here. And notice where it is big and where it is small. And it's flipped. It's unusual, right? But there is a purpose and a reason behind it. And so what our x-axis is representing is binding energy. And binding energy is the energy that it would take to remove that electron from this atom. Okay? So if I have, here's my positive nucleus, and then my energy levels here. And let's put 2 electrons over here. Now, another name that's almost identical, if not identical, to binding energy is ionization energy. And again, it's like, how much energy do I have to add? Because remember that these electrons are negative and this nucleus is positive. So it's like a magnet. There's an electrostatic attraction to them between these two things. And that if I go and I grab onto this electron, it's going to take energy to be able to pull that away from the atom, right? And then once that electron has been removed, that's what the ionization energy is, or the binding energy is. Now, my question for you, though, is which electron do you think takes more energy to remove? The one that I've just circled, let's call that electron A, or one of these electrons that's closer to the nucleus there? Which one, electron A or electron B, do you think takes more energy to remove? Okay, now don't forget about Coulomb's law, that this electrostatic force of attraction is equal to a constant, a K value, I'm not worried about that. The charge, this is like the charge of the electron plus the charges of the charge of the nucleus, divided by the distance between these charges squared. And what we'll notice is that with electron A, it was further away from the nucleus. Its distance between these two particles, the nucleus and the electron, is larger. And because it's in the denominator of this equation, that would result in a lower electrostatic force. That the attraction between an electron A and the nucleus is less than the attraction of electron B in the nucleus. The closer an electron is to the nucleus, the more energy it takes to remove it from an atom. Great. So that is the reason why this axis is flipped. Think of it as like the nucleus. Think of it as the nucleus is over on the left here. Okay. That this is where the nucleus is, and then we move further from the nucleus as it goes to the right. Okay. And so the electrons that are represented right here, those ones have higher binding energy, and the reason why they have higher binding energy is because they are closer to the nucleus. And then these electrons that are right here, these have less binding energy than the first one that I drew because they're further away from the nucleus. And we see the fact that of this in their shells, right? This is in that first ring around the nucleus, and these guys are in that second ring around the nucleus because it's a 2s and a 2p, where this one was a 1s. All right, now, last thing about these spectrums. the y-axis. And notice that it says relative number of electrons. Well, 2 class periods ago with Miss Watts, you learned about electron configurations, really reminded about electron configurations. And we saw that when we were in the ground state, that the maximum amount of electrons in the 1s was 2 electrons, right? Like that's our maximum. And so if there is more than just the 1s, like a 1s, 2, 2s, 2, 2p, whatever, we know that the height of this peak must represent 2 electrons, okay? So if that height is representing 2 electrons, and we double that, then this height must relatively be representing 4 electrons. And then if I put another length of 2 electrons on this again, that must be 6 electrons, right? So we have 2 electrons, 2 electrons, and 2 electrons. So this peak over here, that must be 6 electrons in that sub-level. Great. Now, vocab. I said sub-level. And the reason why is because both the 2s and the 2p in this spectrum, okay, so both this 2s and the 2p, those are in the same energy level. It's the second energy level. The n equals 2 energy level. But they are each their own individual sub-level within that level. So we have the 2s sub-level and then the 2p sub-level. All right, great. Well, what atom or element is this electron configuration or photoelectron spectrum even for? So what we see is our 1s, which has a peak of 2 electrons, and then our 2s, which has a peak of 2 electrons, and then our 2p, which has a peak of 6 electrons, okay? Yeah, I'm doing a video right now. And so which element ends with an electron configuration of 2p6? Well, let's see, because I don't have a periodic table on here, so let's pull one of these up. Look, I was trying to figure out how to record this for you guys. Periodic table. All right, so here is the P block. And so what I'm seeing is our 2p6 is neon. We're ending with neon there. No, you're not able to see the stylus on that. That's okay. Alrighty, great. So this electron configuration, and thus the photoelectron spectrum, was for neon, ground state neon. All right, let's try this again. So it says that this is the photoelectron spectrum for lithium. So let's see. Now, energy, and always check this because on rare occasions they do have this as the lowest energy and this one as the highest, but it's really unusual. So find where the energy is the highest and know that that's closest to the nucleus. And so then that first peak needs to be a 1s. So this is our 1s peak, and we see its height, and that height is representative of 2 electrons. And so our next peak must be the 2s peak, but notice that the peak is half as tall, so it has half as many electrons in it. So that means that we have the electron configuration of 1s2, 2s1. Okay? So then, checking our periodic table here, 1s2, 2s1 is our lithium. Wonderful. All right, now, what if, so we're looking at boron. Oh, and then we get a comparative. Okay, great. So one more time, checking on this. When you get to the actual test, it's going to say, hey, here is the photoelectron spectrum, but it's not going to say what it's of, right? It will say, here's the photoelectron spectrum, which element is this? And then there's other types of questions, but I'll show you that in a moment. So again, we find where energy is the biggest, where it's the lowest, and we know that this is closest to the nucleus, where energy is the biggest. So the first peak has to be the 1s, and the height of this peak has to represent 2 electrons, 1s2. Our next peak is 2s, and it's the same height as the first peak, so we get 2 electrons. And then after that, it's the 2p. But how many electrons are in there? Well, if this is the height for 2 electrons, and this peak is half of that height, it must only be 1 electron. So the electron configuration that we're seeing is 1s2, 2s2, 2p1. Okay. Now, please don't forget to check on your periodic table. Like, are we actually getting our 2s1 for boron there? Or sorry, no, 2p1. My bad. So we had a 1s2, 2s2, 2p1. Yep, that looks great. Okay. Now we're going to do some comparative ones here. So there we're seeing a difference here between hydrogen and helium. So the dotted line is either representative of hydrogen's photoelectron spectrum or it's representative of helium's. And we have to decide. And there's actually 2 reasons why I can make this designation and make this choice. So let's talk about it for a moment. If we look at our periodic table and we see the atomic number for hydrogen, I'm going to do these in different colors. So we'll do hydrogen and then helium. Okay. And hydrogen, inside of its nucleus, it has 1 proton, right? 1 positive proton. And without even looking down here, right? Like if I think about this for a second, using my periodic table, I know that the electron configuration for hydrogen is a 1s2, or sorry, a 1s1. Like that's it. So this would mean that there's only 1 energy level, right? Because it's a 1s. And inside that 1s energy level, there is, 1 electron. 1 electron. So I'm going to draw that really quick. I'm going to draw, and I'm going to exaggerate something that I want you to see in a minute. But so I'm going to draw this electron. All right, now over to the helium for a moment. Using my periodic table, I'm able to see that the electron configuration of helium is 1s2, and that's it, right? 1s2. And so that means that there's only 1 energy level, because there's just a 1s, and that inside of that energy level, I got 2 electrons here. I also can see that the atomic number is 2. So inside of this nucleus, we have 2 positive protons, not just 1. And then there's only 1 energy level around it. And there's 2 electrons in that energy level. Now there's a reason why I drew this first energy level, the n equals 1 energy level, further away from the nucleus for the hydrogen and closer to the nucleus for the helium. Why do you think that might be? the main reason for this is due to the number of protons. Like, think of the nucleus as like a little positive center, and this guy has a charge of +1, where helium has a positive, it has a charge of +2. And so it's like the helium is like a stronger magnet, and the hydrogen is like not quite as strong of a magnet. That the attractive force of this proton on this electron is not as strong as the attractive force of these protons on both of those electrons. And they feel it equally because they're equal distance from the nucleus, and because the nucleus has 2 protons. Like, those 2 protons are pulling on both of those electrons with the same magnitude as if there was only one of them, really, kind of. Now, great. So with all that information in mind, is the dotted line hydrogen or helium? So we're going to notice 2 things. The first thing that we're going to notice is that's where my energy is the biggest, so that's where the nucleus is. So this 1s here, for this guy, is closer to the nucleus, and the 1s here is further away from the nucleus. So that would mean that this 1s is closer. Oh, so that must be our helium then, because those electrons are closer to the nucleus due to the fact that the nucleus has a greater positive charge, a greater attraction. So this must be our 1s2, which is our helium, and then this one that's further away, our 1s1, it's half its size, so it has half as many of the electrons, the peak height, I mean, and so that must be the hydrogen. So those are the 2 ways that I can tell. The first one is the distance from the nucleus, and the second is due to the peak height. That in the 1s orbital for helium, it has 2 electrons, so that means its relative number of electrons is twice as much as the hydrogen. All right, lovely. So our first general rule of thumb is when electrons are in the same energy level and the nuclei has a greater amount of protons, then the overall attraction is greater. That means the binding energy is greater, and the distance between the nucleus and those electrons decreases, right? The greater number of protons means smaller distance away from the nucleus and a greater attraction to that nucleus. Now, notice that I did start by saying that these electrons are in the same energy level. Like, these were the electrons discussed for hydrogen and helium are both in the first energy level, because something happens when we get to more than 1, and I wonder if I have a comparative one. No, we'll do it here. It's fine. Something happens when there is more than 1 energy level, okay? So what we're going to do is the current spectrum drawn on the bottom of page 35 is for beryllium, Be, beryllium. And then what we're going to add to this is the spectrum for magnesium. You see magnesium right below beryllium there? All right. And then actually, let me look at this again. So we got a 1s2, okay, yeah. So for beryllium, and I'll do that one in red. According to the periodic table and according to the photoelectron spectrum below, we're going to have a 1s2, 2s2, electron configuration. One, yeah. Oh, look, made it kind of prettier, I guess. I don't know. 1s2, 2s2. So what does that mean for us? The first thing is that we have two energy levels, not just one. So here's the first energy level, here's the second, okay? I also see that in this first energy level, there is 2 electrons, and in the second energy level, there's 2 electrons. All right. Beryllium has an atomic number of 4, so our nucleus is going to have 4 protons. So I'm going to have my 4 protons in the nucleus here, and then I need my first level, and then my second level. Okay. Now, in this first level, there are 2 electrons, and in the second level, there are 2 electrons. Great. What about magnesium? Okay, so let's do this one in blue. So for magnesium, and if you look at your periodic table, you'll be able to follow along, write this electron configuration. So we got 1s2, 2s2, 2p6, 3s2. Okay, that's the electron configuration for magnesium. Now, a couple of things. There are, what was the other color I did? Oh, did I switch them? That's okay. Let's go with the green first. Okay, so we have 1 energy level. We have a second energy level. And then there's also, I guess I'll go with red, a third energy level. Okay, and in this first energy level, there are 2 electrons. In the second energy level, there's 2 plus 6 for a total of 8 electrons. And then in the third energy level, we got 2 electrons. The other thing, let's see, 6. The other thing is magnesium has an atomic number of 12. So that means there's 12 protons in this nucleus, okay? So that's a lot more protons. Got 12 protons in this nucleus. Okay, so I'm going to draw these 3 energy levels, but I'm going to very strategically and purposefully draw these. And the first thing I'm going to do is this n equals 1 energy level is going to be closer into the nucleus than the one for beryllium. Okay, and then that's also going to be true for the second. The second energy level is going to be closer to the nucleus. One more time. Closer to the nucleus. I think it was worse. All right, we're going with it. Closer to the nucleus than the beryllium. But this third energy level, it's going to be a bit further away there. Okay, now let's put these electrons in here. So in this first energy level, which we'd call n equals 1, we also refer to these as electron shells. So that's the first electron shell, this one's the second, and the third one is up there. Okay. So the first energy level we see had the 2 electrons like we were talking about. 1, 2. And then in the second, there was quite a few electrons. There was 6, 7, 8. So 1, 2, 3, 4, 6, 7, 8. All right, lovely. And then the third energy level, there's only 2 electrons here. All right, so why have I drawn this the way that I have? Let's start with the first energy level, this n equals 1. And think about these electrons for a second. For these electrons, we see that there's 4 protons pulling on those electrons. And this is compared to having 12 protons pulling on these electrons. Well, 12 protons is going to pull way stronger than 4 protons will. That's why the first energy level was closer to the nucleus in magnesium than it was in the beryllium. And this logic still stands for the second energy level. In the second energy level, like this electron right here, okay, in this second energy level, there's 2 things happening. First is we have 4 protons pulling on those electrons, pulling it in. And then the second thing is that we have 2 electrons in the first energy level that are trying to push the second energy electrons away. And notice that the number of electrons pushing away is the same on this next one here. That this electron in the second energy level is fighting the same amount of electron repulsion, the 2 electrons in the first energy level. But the number of protons is so much greater that it's going to have a greater attraction. And this is true across for all of the second energy level electrons. They're fighting against the repulsion of the first level, and they're being pulled in by 12 protons. So the overall attraction is greater on the second energy level for magnesium compared to beryllium. But it's the third energy level, something happens. First off, it's just the fact that it exists, right? Like the beryllium didn't even have a third level. So of course, if we're adding another level, we're adding bulk, we're adding distance within this atom. And then the second thing is it's probably even a little further than we might realize, because yes, for this electron, it's being pulled in by 12 protons still, but there is 10 core electrons in the first and second energy level that are repelling those outside electrons. And so that attraction is far weaker. And due to this weaker effective nuclear charge or attraction of the nucleus, the capacity of this nucleus to attract these outside valence electrons, the distance between these valence electrons and the nucleus is far greater. So what we see is that when I draw these peaks for the beryllium, okay, that my first 1s is going to be closer to the nucleus, closer to that higher binding energy. Like there's my 1s2, okay? And then we have the second energy level, which contains 2 peaks here. We got a 2s2 and then a 2p6, which is just going to be huge. Sorry, we're like going off the screen because it's got to be 3 times the size of that first, and even that's not right. Like it should be taller than that. But notice how this second energy level is a greater binding energy than hydrogen's second energy level. And then the last thing we have to do is we have to include our 3s2. And these ones are further away from the nucleus and they have way less attraction, way lower binding energy. And so then, oops, I did the wrong color. And it's got to have the right height as well. That's the peak height that represents 2 electrons. So there's my 3s2. Alrighty. When we are in class, then we're going to practice this some more, where I'm going to give you different spectrums, and I'll have you add a spectrum and see. You're going to have to tell me which side these peaks are to each other comparatively are the ones that you're drawing to the left or to the right of the other ones. And then we got to also consider these peak heights. And so that's what we'll be doing in class when we are back on Tuesday, because remember, Monday's a holiday. Okay, see you guys all.